I'm going to introduce our next speaker. Carl is CEO of Autodesk, has been an entrepreneur, got acquired by Autodesk, but more importantly, is sort of a maker and a builder himself, building stuff all the time, I'm told. Come on up, Carl. Carl's going to talk to us about another major direction, which is 3D printing, IoT, all this physical world stuff that's starting to change in more radical ways than I've seen in a long time. All yours, Carl.
Okay, thanks, Vinod. Good morning, everybody. So I am going to talk about 3D printing and why it matters, but kind of try to do it in a broader context of the blending of atoms and bits, and I'll talk about that. Let me just give you a little bit of background, because many of you have started companies or starting companies. I work at Autodesk. Autodesk has close to 10,000 employees, but started with 16. It had $10,000 of investment in a single product. So 30-something years ago, 16 people and $10,000 started the company, and that's what it is. That's what it is today. For those of you who don't know anything about it, what we do is we make design engineering software. This is the range of stuff we do. It's software for media and entertainment, software for manufactured products, and most of the built infrastructure, roads, bridges, but it's always design and engineering software. And generally speaking, historically, we help customers do something on that side of the screen. We got them all the way to the point of having a digital prototype of what they were going to build. And only in the last half a dozen years have we kind of switched it around to say, how do you take it from that side of the screen to this side of the screen? As Vinod said, I've been a maker my whole life. For 40 or 50 years, I've been making stuff. I've designed sailboats. I've built sailboats. I've built furniture. I've built houses. I've built machines. Not particularly attuned to any one thing. If I see something, I always think there's a way to build something, and generally I have this idea that I can make it better. So I'll tell you about 3 projects I've been working on lately. One, this is with my younger son. So my younger son decided we needed an electric go-kart, and so we built an electric go-kart. It's got about a 20 horsepower electric motor. It comes from the guys at Lightning Motorcycles. This go-kart is geared to go about somewhere between 60 and 70 miles an hour. It was totally cool. He built it about 3 years ago. This summer, we were actually driving it and flying a drone overhead and filming it. And we decided, instead of the drone following the go-kart, what if the drone could drive the go-kart? So we now have an autonomous go-kart. We just took the guts of the drone and transplanted it in there. You can see, like in the front, that big red servo sitting on the front and connected up to the electrical system. And next week, with a whole bunch of startups, we're going up to Thunder Hill and we're going to go race. So there's a whole bunch of startups around the Bay Area all doing autonomous vehicles. I'm sure, ours is the most ghetto of the vehicles up there. Everyone else has spent tens of millions of dollars building their autonomous vehicle. We've probably spent a couple $1,000 building this thing. So that's one of the things I'm working on. This is another one. Is my friend Benny here? Where's Benny? Hey, Benny. I'm not trying to compete with Benny, but this is my attempt to build a metal 3D printer. So this is taking a microprocessor and a CNC control and hooking it up to a MIG welder. And so I'm now printing steel and bronze and aluminum. This is a steel thing. It's about this big, and it prints in about 25 minutes. Benny's doing much cooler stuff. I'm not here to compete with Benny. And the third project I thought I'd show you about right now started with this idea. There's a little sensor over there. This all started, I was milling something on my CNC machine, and something was going wrong, vibrating terribly, and I said, turn the knobs for feeds and speeds, and wasn't getting it, and I felt like I'm kind of a blind man walking out there trying to figure out what to do. So I did what reasonable people do, is I took my cell phone, I put it in a Ziploc bag, I taped it to my lathe, and then I recorded the signals and I put it through signal processing software. And now there's a small company called Infinite Uptime that's a startup that's doing this. And that's a little device. It actually, the red and green tells you whether the tool is sharp or dull. Obviously, you can do a lot more analytics on it. But this all started with just a Ziploc bag and a cell phone. So those are the 3 projects I've been working on over the last few months. Okay, one of the things we're doing kind of as a startup, as Vinod said, I got to Autodesk. I've actually got there, I started 2 startups and I sold them both to Autodesk. And after 2 times of selling, I kind of gave up. And so the startup we're doing inside is doing cloud-based engineering software. All those projects were done with it, and I just thought for people who are building hardware, one thing is it's free for software. So that's my advertisement for the day. So you should look at it. But the basic idea was, how could you use cloud-based engineering software, go to all the way from concept to fabrication? Because everyone in the world is trying to figure out how can they shorten that time and how can they get products that are differentiated. And so that's our inside startup. Okay, let me talk to you about why I think 3D printing is interesting. Starts with this basic idea that I think we have for 30 years treated computing power as though it was precious. And really, it's incredibly cheap and plentiful. If you look at all the assets known to us, it's the only asset that's cheap and getting predictably cheaper. Yet we continue to think of it as precious. Like right now, I can rent a CPU hour for 2 or 3 cents. For a cup of coffee, or 100 CPU hours. And next year, it's going to be 200 CPU hours. But when you look at product development, I don't think people are really taking advantage of that yet. So as you think about that, that's one of the reasons that's in the background of what I'm going to describe. When we think about 3D printing, this is not what I'm thinking about. I am totally uninterested in plastic tchotchkes. Maybe somebody should be building, printers for it. It is not an interesting market. As we move to interesting material science, things like composites, things like metals, we will get to the point where right now we're only at really prototypes, moving right now into high value, low volume things, but it will eventually move into the mainstream, certainly in terms of jigs and fixtures and intermediate products, and finally to the world of volume, valuable products, distributed on a massive basis. Here's one of the things I like about 3D printing is, and people have talked about it. I think when you weigh it out, there are 2 things that are going on. On one hand, shape complexity is free. For people who make things, having a machine that's willing to print something as complicated as that or that or that, as easily as it prints a cube, sometimes more easily than it prints a cube, is an incredible liberating thing for a designer or an engineer. On the other hand, the problem with 3D printing, generally speaking, it goes up as the power of 3. So that if I want something twice as big, it takes 8 times as long. Both of those things are true, and are going to be true for as long as 3D printing is there. Where we are right now, in my mind, in 3D printing, it's probably for those who are old enough to have been there, feels like, the early 80s. It's like the first PC companies. And yes, there have been a few successes, but we are still really early. And I think if you look back 10 or 20 years from now, you will see that these are just the very beginnings of what's possible. Okay, so what's interesting to me is these new techniques in which we can fabricate almost anything and the power of computing, this virtually infinite computing. And it leads to something called generative design. What's interesting about this is a heat exchanger. Nobody designed this heat exchanger. Not at all. What was done, this was described by an engineer in terms of the space, thermodynamic requirements, and the computer entirely generated this by itself. Came up with tens of thousands of iterations, used tens of thousands of CPU hours, but remember, they cost 2 cents. It's not a bad thing to do. And what I think that's interesting about it, because of the technique that's used, you end up with a nearly optimal answer. And I think it's particularly beautiful as well. So this idea that we're going to be able to use computers in which we specify the outcomes we desire, as opposed to start with kind of blank sheet of paper and start drawing and modeling stuff, or writing equations. Instead doing this, I think it's going to be a breakthrough. Here's some work we did with Airbus. And this was imagining the aircraft of the future. So rather than starting with a pressure vessel like a submarine and putting wings on it and calling it an airplane, which is what we've been doing for the last 50 years, this was one of the promises of 3D printing, which is I can put material anywhere in space I want to. And when you look at that airplane, you can see the parts that are clearly structural and the parts that are not. And that's one of the things that we can use software to determine. One of the things we did, because that plane that Airbus worked on, first time they'll do it commercially is like 2050. And we wanted something more practical. So we worked with them on a partition, that D-shaped partition that has a jump seat. And again, what we did, and today it's actually a composite material, it's a honeycomb, it's actually fine. But we took that, we took the shape of it, we input it to the computer, said it needed a bunch of mounting holes, it needed mounting holes for jump seats, and then we said to the computer, go design a better one. And there it is going through thousands and thousands of iterations. We came up with one that was about half the weight and actually stronger than the original. And what was interesting, when Airbus came back and saw the final result, what they said to us is, could you make it any lighter? Because it's a huge difference getting lightweight things into the air. You know, this is essentially taking out millions of pounds of CO2 as a result of being able to fly lightweight parts. And so what we did with this is we said, nah, this is kind of really where it hits the spec. And for anyone who's done engineering, you would understand this. They looked at us and said, by the way, the only reason that's the spec is we built one of these like 30 years ago, and we made it the spec. What if we told you, you know, it needed to resist forces, you know, the loads on it would be 30% less? We were able to go down like 15% more. So we actually, here's actually the testing of it. That was the testing of it. Hardly testing at all. Don't worry about getting in that airplane. It's all good. So anyhow, it did actually get tested. It got fabricated. It was not fabricated in a single part. It was 3D printed in sections out of metal, out of a special aluminum alloy. And it's actually going to get to fly in the A320 this year. So you'll start to see some of this work actually come there. So let me tell you a story. So we started to think, okay, this was interesting, and we got that insight about the specification of how things were built, that they're kind of on paper, they're very officious, but they may not be accurate. So we said, how would you design products in the future, given these technologies of having virtually infinite computing, plus the ability to fabricate almost anything? And so we got together with the Bandito Brothers. The Bandito Brothers are a bunch of people who do stunt driving in LA. And they do absolutely, here we go. Okay, that's the Bandito Brothers. So what we did with the Bandito Brothers, I can see them up here. Can we go back one slide? Maybe. No? It's weird, I can see it here. Anyhow, let me tell you what we did with the Bandito Brothers. We decided to build a vehicle. And so we started out with this idea of building a dune buggy. And we took the dune buggy and we took it out to the desert. And we had the Bandito Brothers drive it really, really hard for 3 days. And we put sensors all over the dune buggy. Every part of this was instrumented and censored. And we took the results of that, and then we said to them, let's take that back, and for the input to this new way of doing generative design, we said, let's not imagine what it is. Let's just take the forces that are involved and input those to the computer. So, okay, so here they are actually driving this thing hard. Like crazy hard. Oh, it was 7 days. Okay, and so then we took this input and we put it into the computer in order to design a better chassis. So again, rather than asking the automotive engineers, what loads they thought that the frame needed to support. What we did instead is we input that, and this is the chassis that was actually designed by the computer in response to the forces that were actually felt during the 7 days of testing in the desert. And so again, it came up with something that's nearly optimal, and again, I think incredibly interesting looking, and probably beyond the capability of almost all of us to design manually. And this to me opens up this door in which I think many of the things that we assume have to be done through manual modeling, we're going to have the same ability to use these kinds of tools and machine learning to design and engineer physical products. Now, the rub in this and why this comes back to 3D printing is most of these shapes are incredibly difficult to fabricate. So if we had to do this through normal means, it would be very difficult. Again, shape complexity is free. The 3D printer doesn't care. And so we're able to fabricate these. If you look, this is one of the models. And one of the interesting things about how we went about developing this framework is we're relatively indifferent to the kinds of solvers that are in there. So it could be a finite element analysis. It could be CFD. This in particular, what we've done is we've shown two different ones. This is done out of an aluminum alloy, and this one is out of titanium. And so you can take into consideration almost any parameter that you can characterize and quantify. And so in this case, the same inputs, same process, but I could actually fabricate one out of aluminum alloy and one out of titanium, and I would actually know the specific properties I'm building into those. So I think this is kind of insight into the way that people are going to design and engineer things in the future. So let me just wrap up a little bit with why I think 3D printing is interesting and also where it's going. So the first one is, when I think of 3D printing, I think there are several things that are going to go on. The first one is, I do not think there is a single technique. Many people are looking for the silver bullet of 3D printing. I think it's going to be a tool. You will have ones that do composite 3D printing, metal 3D printing, plastic 3D printing. There is not one technique that's going to solve it all. But when you put it in a broader context, what I think's really happening is our ability to fabricate things are now being controlled by microprocessors. So it's this general idea of digital fabrication, that we can go all the way from digital design, in fact, design that is done by the computer, all the way through fabrication, so you can get completely through it. And when you look at it, certainly 3D printing is going to be a big deal, but I think subtractive manufacturing is equally important. It is one of the ways that we can make large number of parts at affordable prices. Most interesting to me is the combination of additive and subtractive. One of the limitations of subtractive is that you often don't have access in order to make that complex geometry. But if you only print one level at a time and then machine, and you interlace additive and subtractive, by definition, at any point in time, I have access to all of the geometry, and all I have to get down is 10, 20, 30 microns. I can do that for certain. So additive and subtractive coming together in new machines is going to be a really interesting way. A bunch is going to go on with robotic assembly, and we're already seeing it. I joke about the robots is that robots are what we call something before it does something useful. As soon as it does something useful, we call it an automobile or a vacuum cleaner or a train. But we're starting with the basic idea of robots, and they will become prevalent through most of the manufacturing process. And the last one, which I think is the most promising, and if I was to mimic The Graduate, what I would say to my kids is not plastics, I would say biology today. Because I think one of the most interesting ways we're going to make things in the future is biologically. And we are going to reprogram life forms to actually manufacture. And for the extent that people think that's a little bit far out there, essentially, agriculture is the first form of biological manufacturing. We use it for food and clothing. It's not that great a stretch to imagine that we can do a number of other things with it. So 3D printing matters. It matters much more in an industrial context than it does in a consumer context. And what's really interesting to think about is not 3D printing but itself, but this idea of taking microprocessors and controlling the means of production in order to get high quality, low cost parts. Thanks.
So you can re-articulate this question for me better probably than I can ask, but I have this sense that when you made those designs and they're optimal, there's some implicit assumptions about how the stresses flow, but when you 3D print something, you get shearing in ways that are different than the optimal would be.
Right.
And you can re-articulate it, but how do you make those two things come together so that the actual thing you produce ends up with the strength that the model would predict?
Yeah, and there are two companies here that are doing a good job. One is Velo 3D, and okay, I forgot the name of the other company. Arriva. Yeah, thank you, Arriva. Which, what you have to do is, instead of imagining these homogeneous, theoretically perfect materials, what you have to imagine is that they have properties like they're anisotropic, so they don't align, that there are imperfections that come from the manufacturing process. This is one of the things that, again, if you imagine that you're willing to spend huge amounts of computing power on, and that's why my insistence is, just remember, it's 2 cents a CPU hour. Use it extensively. Almost no one I see uses computing to the full power. So for example, we have a product that does analysis of a plastic injection molding. A job will generally run for somewhere between 48 and 72 hours on dozens of CPUs. If you run it on thousands of CPUs, you can do it in an hour. And if you really want to do it in parallel of multiple designs, in that same hour, I can run 100 designs. It is capable of understanding the defects that will come from injection molding because of the location of the ports, the temperature, the material. Both companies, what I think the breakthrough in each of those is the two things that matter most in the 3D printing companies that both these companies are doing really well is a deep understanding of material science and then the software that drives it. And it's that combination is going to make for machines that work. And so, yeah, you have to understand it fully. We have a small team that's doing understanding metal in that way and another one that's doing it on composites to really understand what comes out of the process as opposed to these theoretically perfect. And like, for example, in the case of the Velo 3D, you can't fight physics. The thermal properties are going to deform the metal, but if you can predict and anticipate it, you can do things differently in advance knowing that. So a lot is just a deeper understanding that we fully have the computational tools to understand and we just have to employ them.
I have a question.
Okay, Vinod.
The big question I have is this transition from prototyping. This new style of manufacturing has worked for prototyping. But the massive, massive change comes if it's manufacturing.
Right. And
so speak to what it takes to go from A to B and this radical transformation.
Yeah. So where I think it has been, and remember, the industry was called rapid prototyping until people figured out that that wasn't such a great name. They wanted it to sound more economically viable than just prototyping, and so it became 3D printing. But today, I would say it's extensively used for 3D printing. Right now, I think we're in the second phase in which there are two things going on. You're starting to see the first attempts to get mass-produced products. You saw Under Armour and a number of the footwear manufacturers do it. There are people doing insoles that are printed that way. But you're at two places where you're still in the prototype and you're moving into, generally speaking, either novel items or high-value, low-volume. So you're looking at high-value, low-volume. So for example, if I want an ear implant, it matters a lot. If you look at things like a hip implant, so for example, getting some of the prosthetic devices, Those are the kind of things where it matters a lot, people are willing to pay a lot of money, and having a perfect fit matters. The next step is the one that I think is the interesting one. My belief is that the next set of products are going to be things that are the intermediate products that are used, as well as some of the things around maintenance. So let me give you a couple examples. There is a couple billion-dollar industry in tooling and fixtures. Intermediate products that are ended up used for things like molding and casting. Very complicated to fabricate the intermediate products. Those are places where being able to do it quickly with high strength, being able to do rapid iteration, we'll go there next. I think that will open the door to commercial, to commercial 3D printing that makes sense. There are some of the, we're starting to see some of the machines out there. The Carbon 3D machines is an example of something that's simulating injection molding, and we'll get to that stage. The next step is getting to where there's products that can be only manufactured this way, because one of the things I think is true is there's a number of techniques that are around in manufacturing today that are very affordable. You're not going to make plastic parts cheaper than you can injection mold it. Toy soldiers come out for a fraction of a penny. And that's why, I kind of poo-poo this idea of let's not try to invent a better way to make toy soldiers. Let's figure out how to do new stuff. And I think this is generally true in almost all the adoption of technology I've seen through the years. People often, when they get a new tool, they try to reproduce the old thing, and they try to make TV seem like radio. This is the same thing, like many times right now, given what's going on in the world of composites. It's interesting to me, I go into car makers and aerospace places, and I walk out and I say, that was a piece of black aluminum. What they really did is they took a design made for aluminum, and they just happened to make it out of carbon fiber. It's ridiculous. To like the trained eye, you look and say, that pocket was there to reduce weight. Making it out of composite with that pocket just makes it hard to do. And so I think we need the set of tools that allow you to design things. I also think where you're going to get to is when I can design, for example, a heat exchanger that has an efficiency that's way beyond any other heat exchanger, or a panel in an aircraft that's substantially lighter and stronger. That's when it moves in the mainstream. If you try to take the new tools and just make the old stuff, I don't think we'll ever get there. Yeah.
Go ahead, please.
Okay.
Go ahead.
Oh, thanks. You showed in the beginning, Carl, some of the artistic things you've worked on in terms of designs. We've talked a lot about kind of computationally optimizing, the tensile strength of different structures, but maybe to bring in what Chris was talking about at the end of the Facebook discussion, what is Autodesk doing around sort of that aesthetic side of design, changing the way that designers can develop, in silico, things like the bench and the house and the other artistic stuff that you showed in the first slide?
So one of the things that I think is really interesting, if you can get to a world in which you can do thousands of iterations, the trick is to build experience and intuition along the way. And, I think anytime a new technology is introduced, there's a whole bunch of people who say, no, it'll never be able to do X, Y, or Z. How will you ever get the aesthetics in there? First thing I would say is there's probably 90% of the products in the world that don't involve aesthetics. So even though, let's say, your car, you care a lot about what it looks like, inside the car, you really care that it functions. So one of the things is maybe nothing we do about aesthetics. The second thing is I am always surprised how limited engineers' understanding of the things they design are. So take an architect or an engineer. Take an architect who put up this building. And you say to them after they worked on it for 9 months, if I rotated this building on the site, would it take more or less energy to heat or cool this building? And they go, that's a good question. And what I'm interested in is tools that work alongside designers and engineers. So as I look at, for example, the thousands of choices that came up with those frames, I understand why some are weak, some are strong, some are hard to manufacture, some are too expensive. because I think it's an incredible tool to build this intuition experience as you go along. And that's what I'm really interested in. I don't know, the much more metaphysical question about will we ever be able to have a computer? It's the same question. Will you have a computer that's able to write a novel? I'm not sure we will ever have something. Although I had this great experience with that heat exchanger. I tend to carry these things around in my backpack. And so I had one, and I was giving a talk somewhere, and somebody sent me a text and said, Lord Foster is over at our office. Would you like to meet Lord Foster? And so there's Norman Foster. And so I went over and we started talking about generative design because, starting all the way back to the British Museum, they did a lot of algorithmic design, and it's probably one of the firms in the world most interested in it. And I took out the heat exchanger, and he turned around, and he looked at it, and he turned to the two guys who run the studios, put it down, and he said, this is our next building. And so I was at least impressed that Lord Foster thought it was worthy of consideration for a building, even though there was no explicit attempt to make it good at aesthetics. Thanks.
Thank you.